Welcome, learners, to another deep dive. Today, we're tackling something that really sounds like it's straight out of science fiction, doesn't it? But it's fast becoming a critical, immediate reality in cloud security. And for those of you navigating the complex world of DevOps and cloud engineering, especially if you're thinking about those high stakes interviews, consider this your personal prep session. We're breaking down a really crucial, forward looking challenge.
That's exactly right.
Yeah.
The challenge we're diving into today is um, really at the cutting edge of cloud security. It's this. How do you actually implement quantum-resistant encryption for data in transit between GCP regions? And specifically, how do you leverage algorithms like, say, Kyber or Dilithium? And then how do you manage key rotation within that whole framework? This isn't just, a knowledge check. It's a question really designed to test your foresight, your practical approach to securing the future. So we're going to break down the why is this so urgent, then the what algorithms are involved, and finally the how does Google Cloud approach this. We want to give you a structured, technically accurate, and, well, a truly human-sounding explanation.
Okay, sounds great. Let's unpack this. We'll start with a concise overview, that quick answer you might need right on the spot. Then we'll go really deep into the technical architecture and finally wrap up with the essential takeaways to make sure you're well equipped to talk about this.
Perfect. So for that quick, punchy answer you might need, here's the essence. Google Cloud's current encryption. It's incredibly robust against today's threats, no question. But the looming shadow of cryptographically relevant quantum computer CRQCs means it's vulnerable to future attacks. The solution involves a proactive integration of these new NIST-standardized post-quantum algorithms. We're talking Crystal's Kyber for key exchange, Crystal's Dilithium for digital signatures. And importantly, this isn't a rip and replace. It's a smart hybrid approach. These new algorithms run alongside the classical ones. All of this is underpinned by really meticulous, multi-layered key rotation schedules and careful performance management. The goal is secure and seamless inter-region data transit, even against those future quantum adversaries.
Okay, that's a great snapshot. Now let's get into the full detailed answer. And to really understand how Google Cloud is tackling this, I think we have to start with the foundational problem, right? Why is this even necessary? I mean, why can't we just stick with our current encryption? It seems pretty strong today.
Right, and that's the key point today. What's truly fascinating, and maybe a bit scary here, is the sheer scale of the looming threat. Imagine decades of digital security potentially crumbling in just minutes. That's the kind of power we're talking about with CRQCs. They're projected to be capable of breaking today's classical algorithms, things like RSA, ECDH, which underpin a lot of our current security. Google Cloud's current encryption, while robust, AES 256 for data at rest, RSA, ECDH for key exchange, relies on mathematical problems that quantum computers are just fundamentally better at solving. So this isn't a theoretical maybe anymore. It's becoming a when, which necessitates this proactive, urgent shift to quantum-resistant cryptography. It's kind of like building a much stronger lock before the master key even exists.
Okay, so our current cryptographic locks have a future vulnerability. What are these new quantum-resistant heroes then? The ones stepping in? And how did the industry even settle on these specific ones, like Kyber and Dilithium?
That's a great question. So the core algorithms chosen are the winners, you could say, from a really rigorous multi-year standardization process run by NIST, the U.S. National Institute of Standards and Technology. They selected Crystal's Kyber, specifically the FIPS 203 standard, for key encapsulation mechanisms, or KEMS.
Chems, that's how you securely exchange a secret key.
Yeah,
Yes.
okay.
Yeah.
It's the mechanism for setting up that secure channel. And then there's Crystal's Dilithium, which is FIPS 204. That one's for digital signatures, making sure data is authentic and hasn't been tampered with. But as I mentioned, the strategy isn't to just throw out everything old. It's a smart hybrid implementation. We're actually running classical algorithms alongside these new quantum-resistant ones.
Okay.
This maintains compatibility, gives us a robust, smooth migration path. Think of it like having two different locks on the same door for a while. One works perfectly today, another built specifically to resist tomorrow's advanced lock-picking tools.
That dual layer approach makes a lot of sense. So it's not a sudden switch, but more of a careful integration. How do we actually do that integration at the crypto level, especially for something as fundamental as exchanging keys securely? You mentioned chems. How does that chemtrans mechanism work in this new quantum-resistant world?
Right, so it follows a well-defined mechanism, chemtrans, which is detailed in an RFC draft EETF lamps CMS Kyber, if you want the specifics. Conceptually, it works like this. When a sender wants to send data securely, they take the recipient's public Kyber key. They use that public key to encapsulate or sort of wrap up a shared secret. This generates a ciphertext.
Okay.
Now, this encapsulated secret isn't the final key, but it helps derive something called the key encapsulation key, or key.
A keek. Got it.
Right. And that KK is then used to wrap the actual working key, the one used for the bulk data encryption, like AES. Then on the recipient side, they use their private Kyber key to basically unwrap that secret from the ciphertext they received. From that secret, they can derive the exact same KEK and then use that KEA to unwrap the working key and decrypt the data.
Ah, okay. So the sender uses the public key to lock a secret in a quantum-proof box, sends the box, and only the receiver with the private key can open it to get the secret. And that secret then lets them unlock the actual encryption key for the message.
That's a really good way to visualize it, yes.
Yeah.
It ensures that the shared secret, which is used to derive the session key, is safe, even if a quantum adversary is eavesdropping.
Makes sense. So how do these new algorithms map to the security levels we're already familiar with, like, 128-bit, 256-bit security?
Yeah, good point. We map these directly. For example, if you need a 128-bit security level, the standard uses Kyber 512. That's paired with HKDF HHA256 for key derivation and AES 128 wrap for wrapping the key. If you need stronger 192-bit security, then it's Kyber 768 with HKDF-A384 and AES 192 wrap. And for the top level, 256-bit security, we use Kyber 1024 with HKDF 512 and AES 256 wrap. And on the signature side with Dilithium, it also comes in different parameter sizes, which directly affects the size of the public keys and the signatures themselves. How much bigger are we talking? Significantly bigger, actually. Dilithium 2, for instance, has a public key of about 1,312 bytes and a signature of 2,420 bytes. Dilithium 3 jumps to 1,952 bytes with the public key and 3,293 for the signature. And Dilithium 5 is even larger, 2,592 bytes with the public key and a hefty 4,595 bytes for the signature. Wow, nearly 4.6 kilobytes for a single signature with Dilithium 5. That's quite a bit larger than traditional signatures, isn't it? For an engineer thinking about this, that's not just a number, right? That size has real implications for the network. Exactly. You hit the nail on the head. A typical classical RSA signature might be, what, a few hundred bytes? Maybe 256 or 512 bytes. These Dilithium signatures are several kilobytes. That significantly impacts network overhead. Think about every TLS handshake, every signed message. It means more data flying back and forth, which translates to increased latency, increased bandwidth consumption, especially for that inter-region traffic where the physical distances are greater. It's a critical trade-off you have to manage, getting that quantum resistance versus maintaining optimal network performance.
It sounds incredibly complex to weave these new algorithms into existing massive infrastructure like Google Cloud, especially with services like Cloud KMS and HSMs already in place.
Yeah.
How does GCP actually integrate these advanced concepts without, breaking everything or causing major disruptions?
Yeah, that's a really important question about the practical, real-world integration. The strategy relies heavily on deep integration with Cloud Key Management Service, Cloud KMS, and the underlying hardware security modules, or HSMs. A critical design principle here is strict regional key isolation.
Meaning?
Meaning keys generated inside a Cloud HSM, in, say, US Central 1, cannot be extracted as plaintext. They literally cannot leave that HSM or that region.
Okay, physically bound.
Physically and logically bound. Plus, these HSMs are FIPS 142 Level 3 certified. That's a very high level of security, ensuring tamper protection. We also have multi-party authorization controls, so no single person can compromise the system. You need multiple approvals for sensitive operations. So the implementation pattern involves generating those Kyber key pairs directly within each GCP region's HSM cluster. That facilitates the secure key exchange across regions using these hybrid protocols. And for signatures, the session keys get encapsulated using the recipient region's Kyber public key, while the signature verification relies on Dilithium public keys stored securely in regional key rings within KMS. It's all about keeping that most sensitive cryptographic material within the most secure, geographically isolated boundaries possible.
So the keys live their whole lives inside these secure regional vaults. Makes sense. What about the communication itself, the transport layer? You mentioned TLS earlier. Are modifications needed there? How does that work?
Yes, absolutely. Transport layer modifications are essential. The primary approach is using custom TLS extensions. We implement what are called hybrid cipher suites. These suites explicitly support both classical algorithms like ECDH and post-quantum ones like Kyber within the same connection.
Ah, so the client and server can negotiate.
Exactly. There's a negotiation protocol built in that allows them to agree on using the hybrid approach if both support it, or gracefully fall back to classical only if needed, especially during the migration period. And crucially, as you pointed out with the signature sizes, the certificate chain itself needs modifications. Standard X.509 certificates weren't really designed for multi-kilobyte signatures, so the format and handling need updates to accommodate dilithium.
Okay, so it touches everything from the HSMs up to the TLS handshake and even the certificates. Now, with all these new keys, Kyber keys, KDKs, session keys, key rotation must become even more critical, right? And probably more complex. How is this managed, especially to avoid any downtime for users relying on this inter-region communication?
You're absolutely right. Key rotation is fundamental, maybe even more so now. Our framework is designed for automated rotation and, critically, zero downtime handover. It's a multi-layered schedule. Session keys, the ones used for actual data encryption, are very ephemeral. They rotate frequently, maybe every 1 to 4 hours, often using existing AES 256 mechanisms.
Okay, short lifespan there.
Very short. Then you have the Kyber cake keys, the ones used for wrapping the session keys. These have a longer life, rotating perhaps every 30 days, and they use a crucial 7-day overlap period for transition. Dilithium signing keys used for authentication might rotate every 90 days, again with careful management, like certificate prepositioning. And finally, the root HSM keys, the absolute foundation of trust, undergo a much less frequent, maybe annual rotation involving extensive planning and validation procedures.
That overlap period you mentioned for the KE key sounds vital for avoiding downtime. Can you walk us through how that actually works in practice, say, for that 30-day rotation?
Sure. It's a carefully choreographed process. Let's take that 30-day Kyber cake rotation as an example. Days 0 through 7. The old keys are still active and used for new encapsulations. But during this week, the new keys are generated and securely pre-distributed across the entire infrastructure. Systems learn about them, but don't use them yet.
Okay, pre-staging.
Exactly. Then, days 7 through 14, this is the main overlap, systems start preferring the new keys for encapsulation, but they must still be able to decapsulate using the old keys, because messages encrypted with old keys might still be in transit.
Right, handles any lag.
Precisely. Then days 14 through 21, the new keys become the primary, mandatory keys for encapsulation. The old keys are now only kept around strictly as a backup for decapsulation, just in case. And finally, days 21 through 30, the old keys are fully deprecated and removed. Only the new keys are active for both encapsulation and decapsulation. And this whole dance is coordinated regionally, often using staggered schedules so not all regions rotate at the exact same second. Plus, there are constant health checks and automated rollback procedures built in just in case something goes wrong.
Wow, that's intricate. It really sounds like you're playing 4D chess against future quantum computers while juggling live traffic. My immediate thought, hearing all this complexity, the bigger keys, the hybrid handshakes, the intense rotation schedules, is performance. Will this slow everything down noticeably? What's the real performance hit?
That's the million-dollar question, isn't it? And yes, there is a performance impact. It's unavoidable with current PQC algorithms. Just looking at raw computation, Kyber 768 key generation, even with AVX2 optimization on modern CPUs, takes around, say, 250,000-ish cycles. Encapsulation is more like 530,000 cycles, decapsulation around 180,000. Dilithium 3 signing is also up there, maybe 530,000 cycles, with verification around 180,000.
Compared to classical algorithms.
Significantly more computationally intensive. Classical ECDH or RSA operations are generally much faster. And beyond the raw CPU cycles, there's the network overhead we already discussed. Those larger dilithium signatures mean bigger certificates. The hybrid negotiation adds potentially extra round trips to the TLS handshake. Overall, you might see something like a 2 to 3 times increase in the size of the key exchange messages during the handshake.
Okay, so it's a measurable hit on both compute and network. How do you mitigate that? I mean, you can't just let inter-region traffic grind to a halt.
Absolutely not. Mitigation is key. It's a combination of things. Part of it is optimizing the implementations themselves, using things like AVX2 instructions where possible. Part of it is hardware acceleration, potentially offloading some of these heavy crypto operations to specialized hardware, maybe even within the HSMs or network cards eventually. And part of it is intelligent system design, for example, our defense in depth strategy. We might mandate double encryption for highly sensitive data, pairing classical with PQC.
Right.
We use independent key hierarchies to avoid single points of failure. And critically, we focus on side-channel attack mitigation.
Side-channel, like timing attacks.
Exactly. Things like timing attacks, power analysis attacks. If an operation takes slightly longer, depending on the secret key bits, an attacker might infer the key. So we use constant time implementations. These are carefully crafted versions of the algorithms where every operation takes the exact same amount of time, regardless of the secret data being processed. It makes those kinds of attacks much, much harder.
Fascinating. It shows the level of paranoia needed, anticipating every possible angle. This is clearly a massive shift, not just a minor update. How does a huge organization like Google Cloud actually roll out something this significant across its global footprint? What does that migration strategy look like in practice?
It has to be a very carefully planned, phased rollout. You don't just flip a switch globally for something that's critical. Phase one typically involves implementing this hybrid mode in isolated development and testing environments. You hammer on it, try to break it, measure performance.
Get the kinks out.
Precisely. Phase two might involve enabling PQC algorithms for less critical internal workloads first. This gives you real-world operational data at scale, but with lower risk. Phase three is where you start mandating quantum-resistant encryption for sensitive data flows, maybe making it the default for new services or connections. And eventually, phase four would be the point where you can finally deprecate the classical-only cipher suites once the ecosystem is ready. Throughout all of this, compatibility is paramount. You need that graceful fallback, you need client libraries updated to understand the new algorithm identifiers, and you need continuous, intense monitoring and alerting, specifically looking for any failures related to PQC negotiation or operation.
Okay, that makes sense. A gradual, risk-managed approach. So finally, as you look towards getting this fully into production and keeping it running securely day to day, what are the absolute critical success factors? What has to be right?
Yeah, for production deployment, several things are critical. First, HSM capacity planning. These new algorithms are more demanding, so you need to ensure your HSM clusters can handle the increased load for key generation and operations. Second, network bandwidth provisioning. We talked about the larger message sizes. You need to ensure the network backbone can handle it, especially between regions. Third, updates to the certificate authority infrastructure. CAs need to be able to issue and manage these new types of certificates with PQC signatures. Fourth, robust disaster recovery procedures specifically for this PQC key material. How do you back it up securely? How do you recover it? And overarching all of this is comprehensive monitoring and observability. You need dashboards tracking key rotation success rates across every region. You need performance metrics comparing classical versus PQC connections. You need deep analysis of any connection failures during algorithm negotiation. And you need clear compliance reporting to prove you meet quantum readiness requirements. It's really end-to-end visibility.
That was a truly insightful and, I have to say, incredibly practical deep dive. It really brings home that this quantum threat isn't just theory anymore. The engineering to counter it is happening now.
Absolutely.
Yeah.
And understanding these concepts, it's not just about, reciting technical terms. It's about demonstrating foresight. It's showing you grasp the complexity and the comprehensive approach needed to secure systems against future threats. For you, the listener, especially if you're prepping for interviews, it's about showing you understand the why, the what, the how, but also the trade-offs and the operational realities of doing this at massive scale.
Definitely. We hope this structured approach helps you not only get your head around the topic, but also feel confident talking about it, whether it's in an interview or just staying ahead of the curve in your field.
That's all for this topic. Stay tuned for the next DevOps Cloud interview question.